Hello, my name's Oshin. I'm the corresponding author of this publication, which describes cystine crystalline nucleation and decay in the context of cystinuria pathogenesis and treatment. Of course, my PhD student, Kimberly Noble, worked alongside me and she did a lot of the heavy lifting in this publication. But I'm going to talk about some of the key findings and interesting points in our publication for this series for the Royal Society of Chemistry for emerging investigators. Cystinuria is an inherited disorder affecting cystine reabsorption in the proximal tubule. Two genes are implicated, SLC3A1 and SLC7A9, which encode for these two subunits which form a heterodimer. And it's these subunits, when they form this heterodimer, which enable cystine reabsorption in the kidney. And of course, if they're not encoded because of a genetic predisposition, there's increased cystine found in the urine. This cystine can, of course, become supersaturated and can form crystals, which can cause damage to this sensitive apparatus. So one of our first objectives was to try and understand the conditions that enable these cystine crystals to form. And really our key aim or objective in this first part, if you like, was to try to recreate those classical hexagonal cystine crystals that are found so often in the clinic. And we can see here that between supersaturations of 11 and 8, we reproducibly and relatively quickly find our target morphology. We also see that these hexagonal habits of cystine can also stack on top of each other. They can homogeneously nucleate, and this can form rosettes. And you see lots of beautiful images in the publication of these cystine rosettes forming, all based around this hexagonal plate. We spent a long time looking at these cystine crystals under the microscope, and we see that after rapid precipitation, this hexagonal face is exposed to the viewer, and this represents the 0001 set of faces. Whilst if these crystals, these plates, are allowed to mature over several weeks, as you might find in a cystine stone, we see these large columns of cystine begin to form. And these are exposing predominantly the 101 set of faces. You can see that these are six-sided and, of course, they're symmetrical. And when we look closer at these cystine crystals, we start to really get a sense that they're made of these individual layers, if you like, of these hexagonal plates. When we look at them along the column, along that 101 phase, we get a sense that there's perhaps lots of dislocations between each of these cystine layers. And indeed, these dislocations enable the cystine crystal to be easily cleaved with a razor or a spatula tip. Our second part, our second key finding in this paper, was to explore how agents that are postulated to work indeed do work and are also being explored in clinical trials to find out how these crystals and how rapidly these crystals of cystine dissolve in their presence, or in the presence of these agents. And briefly, what we find is that pH-mediated dissolution by cysteamine and sodium bicarb, it's much more rapid than the disulfide-mediated exchange from our other free thiol containing agents. And this is perhaps best evidenced by the difference in the rate of dissolution for cysteamine when we adjust the pH from 9.7 to 6.9. We can see that that pH adjustment eliminates that rapid pH-mediated decay of cystine in the presence of cysteamine. Of course, disulfide exchange will still happen, but this rapid pH-mediated dissolution will not. And so that concludes this short video summarizing some of the key points of our study. I hope this has piqued your interest a little And you can find, of course, much more detail on the publication, which is published in RSC Advances. Thank you very much.